Howdy, Mr. Russell here, and let's talk about some heats of fusion and vaporization, plus some calorimetry. Please watch this video. I recommend this video by Tyler DeWitt. It's called Phase Changes, Exothermic or Endothermic. And he really walks through some counterintuitive processes of three different phases of water: ice, water, and steam. And if you really think, is ice melting to water, is that an exothermic or endothermic process? You think that something that gets warmer is going to be an exothermic process. That's what most people will think, although it is actually an endothermic process. Because if you think about the system itself, the water molecules itself, they are actually absorbing energy from the outside, so they are moving faster and moving at a higher temperature. That's what causes them to go from ice to water. So the phase change from ice to water is an endothermic process, and then water to steam is endothermic. Going the other way is actually exothermic. Steam to water and then water to ice is exothermic, going this way as it cools. We can actually quantify these mathematically by things called the enthalpy changes of fusion and vaporization. So these, the ones in green, are these fusion ones are going to be where it fuses, goes from the solid to the liquid phase, that phase change right there. And these here are going to be from the liquid to the gas phase, the vaporization. And notice that water it takes about 6 joules per mole to change ice to water, and it takes about 40 kilojoules per mole to take liquid water to steam. You'll notice that they all have different heats of fusion and heats of vaporization, or enthalpy fusion and vaporization, and that has to do with their different boiling points. That's where we get that from. We can quantify these the heats or the changes in heat flow by a process called calorimetry, where we're actually measuring the calories. I'll explain in just a second what a calorie is. So when a hot object is placed in cool water, we will actually heat up that water, and we can measure the difference between how much we can measure using this thermometer, how much the change in the temperature of water. Then we'll know the change in kinetic energy, and we can use some formulas in math to calculate the enthalpy in the heat. We use this calorimetry to find the delta H, or the enthalpy in a chemical reaction, using the heat involved in a chemical change. To calculate this, we'll have to take into account a certain constant value that's individual for every unit, and that's called the specific heat. It is specific to each substance. So, and water has its own specific heat of 4.18 joules per grams degrees Celsius. This is a value that is not on the AP formula chart, but and I guarantee it will show up on the AP test. So you want to commit that one to memory for sure. Here are some constant values of some different substances, 7 different substances. Notice that water is 4.18. It's also the highest number. And water is 4.18 is going to be one of the highest specific heats that you'll find, and the highest one that we'll find in our high school lab. Mercury is one of the lowest ones that you'll find, 0.14. So you may have wondered, when am I going to get back to that calorie? The specific heat of water, I'm going to go back one slide. Specific heat of water is 4.18 joules per grams degrees Celsius. Now, the English unit for this is actually 1.00 calories per grams degrees Celsius. So what they're doing is they're interchangeably using joules or calories. Since the English units and the standard units are different, and we want to all be on the same unit, we'll really just consider joules, and we'll just use joules. But that's where the name calorimetry comes from, is because we're going off of the calorie. So the energy released in the heat can be expressed by this equation. Q equals mcat. I like to, Q is the heat, equals the mass times the specific heat times the change in temperature. This is a long example, so I'll let you pause and read. But look for what is asking for. What value is it asking for? It's asking for the specific heat or the heat capacity per gram of molybdenum. So let's try to go through these and underline which ones apply to water and which ones apply to molybdenum. First, I will go ahead and post the answers here so you can see them, and then I'll explain. So a coffee cup calorimeter contains 150 grams of water at 24.6 degrees Celsius. This one refers to the molybdenum heated to 100 degrees Celsius. Then they're placed in the water calorimeter, and the contents of the calorimeter come to a temperature of 28 degrees Celsius. Okay. So let's go ahead and underline what pertains to molybdenum. 100-gram block of molybdenum, and then 100 degrees Celsius is molybdenum. But then it also ends up at 28 degrees Celsius. So this 28 degrees Celsius applies to two different values. It applies to the final temperature of the water, but also the final temperature of the metal. So now when I look at this, I apply the Q equals MCAT. Q equals 150 grams of water times the specific heat of water. You have got to memorize that one. And then the change in temperature is 3.4 degrees Celsius. That means that the temperature went up 3.4 degrees. So my change is 2,132 joules. That equals the heat released by the molybdenum as well. So that's a nice key. This is the key step right here. This is the key step, is by setting these equal to each other. 110 grams of molybdenum times the specific heat times the change in temperature here of 72 degrees Celsius will give me my specific heat of 0.27 joules divided by grams degrees Celsius. This is a problem that you will have to do in your inquiry lab, where we have 4 grams of ammonium nitrate are added to 100 milliliters of water in a polystyrene cup. I'll let you read the rest. Go ahead and see if you can work it out. We're looking for the heat of solution in kilojoules per mole. So that should give you a clue what your unit should be or on your final answer. I want you to assume that the heat absorbed or released by the calorimeter is negligible. That means that the percent error is going to be negligible. So we're still going to use the Q equals MCAT rule. and we're still going to find the heat Q. I know the mass of the water plus the ammonium nitrate is going to be 104 grams. You notice you have to be real nitpicky on these calorimetry questions and really understand what it's looking for. Because when we add this ammonium nitrate to the water, it's going to dissolve. So we're seeing how much heat is absorbed when we dissolve a salt. We see the grams times the specific heat of the water times the change in temperature. And we calculate that is 1.39 kilojoules absorbed. So now I have the heats, but that doesn't tell me the kilojoules per mole. So let's go ahead and find out how many moles of ammonium nitrate we have. Use some simple stoichiometry by taking our grams of ammonium nitrate, and we convert our grams to moles and find out that there are 0.05 moles of ammonium nitrate in that solution. So if it's just kilojoules per mole, all we have to do is take 1.39 kilojoules and divide it by 0.05 moles, and we get 28 kilojoules per mole of heat that is absorbed. So it's important to know the difference between an extensive property and an intensive property. An extensive depends on the amount of substance, and intensive doesn't depend on the amount. So the heat of reaction is an extensive property, so that is my Q, and the temperature is, or my T, or my delta T rather, is going to be intensive. It does not depend on the amount of the substance that's present. That's all I have for this video, so thanks for watching. Make sure you check out Tyler DeWitt's video on exothermic and endothermic. He also has some good practice problems that really help out a lot if you need some help with the math.